In an ideal situation, the total amount of energy will stay the same as this girl is sliding down the slide. But in reality, friction will be acting, and that will affect the motion, and therefore it would affect the energy of the system. So when you have an outside force outside of the system acting, the energy of the system changes. In the case of friction, we will talk about thermal energy being dissipated or removed from the system. It is stored instead in the motion of particles. It's a kind of a chemistry idea, and in the bonds between different atoms of like maybe the slide or of the air. But what we see it as is a temperature change. So something outside of the system increases in temperature because energy has left the system and moved into that other object. So, looking at how energy flows into and out of the system, friction is something that takes energy out. But if you think about it, this girl needed some sort of energy input in order to get her to the top of the slide. If she has potential energy at the top of the slide, that energy had to come from somewhere. We use the term work to describe energy that's either being added into or taken out of a system. And it always requires some sort of outside force, some sort of external force that causes this change to happen. So work is defined as that amount of force that's acting times however far the object moves while the force acts. So D is going to be our displacement. Work can be positive or negative or zero. If it's positive, then energy is going into the system. If it's negative, energy is coming out. And if it's zero, it means that there's no change to the energy in the system. Again, just to make sure we're clear on this formula, W stands for work. It's an amount of energy in joules that is the energy given to or taken away from the system. And it depends on how far the object travels, its displacement, which we'll call D here, and how much force is acting on the object from the outside, F. Because it's an amount of energy, it is measured in joules. So, knowing the amount of force, the amount of displacement, we can determine this amount of energy that's going into or out of the system. But we could also look at the effects of that work. We could chart out, we could look at the scorecard of how much kinetic energy and how much potential energy there is at one time and another. And we can see what the change is. And if we see that energy, that total energy increase, then we know work has been done to put energy into the system. Where if we see the total energy decrease, there must have been negative work taking energy out of the system. Let's look at a few examples of positive work. So if you push an object and your force is directed with the motion, that is positive work. It could be a vertical motion instead. So when you lift something, you exert an upward force on the box. Your force does positive work on the box, moving it upwards. In the first case, the box gains kinetic energy. That's the type of energy that has been increased. In the second example, the box gains gravitational potential energy. But in both cases, what's happening here is the force points in the same direction as the displacement, and positive work is being done, meaning a positive change in energy. By the way, we will look at more complex situations in the challenge questions of this unit where things do happen at an angle. But for right now, we'll focus on things that are either directly with or against the motion or perpendicular to it. So let's look at some examples of negative work. What does that look like? Well, the girl sliding down the slide, she's moving down the slide. Friction would oppose her motion in the other way. friction would do negative work. It would take energy away from the system. If you're driving a car, there's always going to be friction that works against the system, pointing against the displacement. You're probably getting the theme here. Friction is the main way of negative work being done. It could also be air resistance. So if you have someone parachuting and they are moving downwards, there is going to be a force of air resistance pointing up. And so that air resistance force does work on the object's motion. In all these cases, it's how the direction of force is opposite the direction of displacement. And in all of these situations, we would say the work was negative, less than zero, and the change in energy is also negative. Negative work means a negative change in energy being taken out of the system. The other possibility is that there could be zero work. For instance, if all you're doing is holding an object, you are exerting a force upwards to hold up a box or something. But if the object doesn't actually move, if displacement is zero, then there's no work done because the energy isn't changing. Or maybe you are moving, but your motion is perpendicular to the force. So this girl is holding a pile of books. She exerts an upward force to support those books, but her motion is to the right. If her motion is perpendicular to the force, then her force doesn't transfer any energy, and the work done by it is zero. Another important example is something going in a circle at a constant speed, like a satellite that orbits the Earth. The inward force of gravity is perpendicular to the motion at any particular moment. So there is no work being done by gravity, no change to the object's energy as it orbits around the Earth. It maintains a constant speed, a constant kinetic energy. So zero work means no change to the energy. All right, the last idea is that it's not always just about how much work is done, but also how quickly it's being transferred, the rate at which the work is being done. So here we have two situations nearly identical, except the one guy's wearing a hat. But they both exert the same amount of force upwards, and they both move the box the same distance. So the work would be the same. But if the person on the left does the job in 1 second, and on the right, he takes 2 seconds, there's something different about this. Even though it's the same amount of energy being transferred, the guy on the left is doing it much more quickly. That has to do with power. Power is not really just about energy. It's about how quickly the energy is being delivered or transferred. So the guy on the left is more powerful. He's able to do the job in less time. And so that involves a greater rate of power. So as a formula, power is work over time, but since work is the change in energy, it's also delta E over time. And again, that delta E could be a change in potential energy, like it is here, or it could be a change in kinetic energy. Power is measured in joules per second because it's an amount of work divided by an amount of time. And that combination of units is called a watt. You've probably heard of watts before with light bulbs, okay? It is talking about that same sort of thing, how much energy per second a light bulb is giving out. We'll talk about that type of energy a little bit later in the class. By the way, also, horsepower is often used to describe power in our everyday world. A horsepower is actually quite a few watts. 1 horsepower is 746 watts. So the second video, we'll talk more about how to use these formulas in our calculations.